We're here at DesignCon 2017 at the Santa Clara Convention Center in Santa Clara, California. DesignCon is the largest and most prestigious conference dealing with printed circuit board design and manufacturing, mainly in the field of signal integrity, as well as covering topics that relate to electromagnetic compatibility, or EMC. The brightest and best engineers in the country present papers. This is more of an applied engineering conference than the IEEE conferences, which are very heavily weighted in the academic. However, the IEEE EMC Society, which I'm a member of the board of directors, is moving more into the signal integrity, and their conferences are now called the IEEE International Symposium on Electromagnetic Compatibility and Signal and Power Integrity. Signal and power integrity is real critical. That's the heart of our business. DesignCon focuses on the SIPI, which is the acronym for Signal Integrity and Power Integrity, and how we can make our products work with new technologies, higher speeds, and greater complexity, and do it at low cost. DesignCon hasn't changed that much. It's pretty much the same, except the technology has advanced significantly from what was offered then versus now. The software, the simulations, instrumentation, instead of worrying about 1 and 2, maybe 6 gigahertz systems, we have 100 gigahertz, even higher. So how do we work with systems that are getting that fast? And we're now getting into technology where our signaling rate is going to be in the femtoseconds. And most engineers can't even conceive of a femtosecond. So in the future, what will our printed circuit boards look like? They'll be fiber optic. We already have fiber optic backplanes. What about nanotechnology? How will that affect signal propagation, material science? So there's a lot of cool things coming out there. And every year, they figure out something new, and that's what's exciting about coming to DesignCon. The topic EMC Made Simple presents an introduction for those who never studied electromagnetics, but need to solve what is considered to be the art of black magic. But in reality, it's not black magic. Everything can be solved mathematically and in a very simplified manner. The content of the tutorial that was given on Tuesday here at DesignCon is based off of contents from this book that I authored, which is actually my 5th book in a series on electromagnetic compatibility, mainly printed circuit board design, as well as testing for EMC compliance. The book and the course has a target for those that never studied electromagnetics, but need to solve a problem quickly and easily and at low cost. It's basically taking Maxwell's equations and in a visual, conceptual manner, and that's the key. You have to visualize what Maxwell tells you. Not worry about what the equations look like, or as a friend once called them, squiggles. But every equation tells a story. And if you can understand the story, you can convert it into simple algebra. And the key item that I was trying to emphasize about EMC Made Simple, or electromagnetics made simple, is Faraday's law, transmission line theory, but you do it in the time domain instead of the frequency domain. Maxwell talks about field propagation using electric fields, magnetic fields, and current. But he does not speak about voltage, which is real interesting, although it is implied in one of the equations with a minus sign in Faraday's law. So if we understand Faraday's law, which is time-varying current in a transmission line creates time-varying magnetic flux, or the right-hand rule, we can easily look at a printed circuit board. Here's my transmission line. And Faraday's law, reduced to simple algebra, is simply L dIdt. Time-varying current in a transmission line, the L dIdt, equals an electromagnetic field. so we can simplify the complex math into a concept that allows us to visualize and solve EMI problems at a visual approach. There's a lot more that I go into in detail, which has never before been published, such as how common mode current is actually created. What causes the arrows? We know differential mode and common mode. How does the arrow physically flip? It's never before been published. And when I talk to academic professors, they realize, I never even knew this, and they have to redo their course based upon the concept. So what was presented at DesignCon was the fundamental of signal integrity, the fundamentals of electromagnetics, simple suppression concepts, how to handle transmission lines, shielding, and filtering. And that's just a very brief overview. There are three basic areas designers need to be aware of in order to ensure that their design meets all functionality, basically both signal integrity and EMI compliance, which is, one, having a stable power distribution network. Make sure that the power and the return planes, and you notice I don't use the word G, the word starts with G, or ground, because ground does not exist in an electrical product. For example, as a battery, you have positive and the negative terminal. So you have to have a stable power distribution to keep those planes, source of sinking, from bouncing, because if they bounce, it creates an unbalanced situation. That bounce propagates on the board, can hit the edge of the board or other components, and now you start getting modulation at RF frequencies. So that's number one, having a stable power distribution. The second, optimal RF return path. Based on the right-hand rule, or Faraday's law, when you have time-varying current going in a direction that creates time-varying magnetic flux, if you have the current go in equal opposite directions, they cancel out. So the object is to make sure that the AC current, and there's a difference between AC and DC current. DC goes the path of least resistance. AC energy, electromagnetic field, will propagate any way possible. And if we bring those two fields together, they cancel out. The third and final item that engineers need to be aware of, especially board designers, is referencing or grounding. Everything in the entire world is single point grounded. And from my viewpoint, there's no such thing as multi-point grounding. The correct definition is multiple connections to a single point reference. Because you have to have a reference based on a voltage, and if you have the reference, you can now send the signal and it knows how to communicate. But if our referencing is off, we have a differential in the voltage level, and the magnitude of that differential through the inductance creates unwanted common mode. Common mode is created as a result of mainly too much inductance in a transmission line, or the drop and the losses that occur from transitioning between layers on a printed circuit board through vias, or going from a nice thick trace into a silicon device with bond wires, real small bond wire. The bond wire creates the EMI. So how do we solve component radiation? So to summarize, what engineers need to be aware of is having a stable power distribution network, providing an optimal RF return path to cancel the unwanted magnetic flux, and to have a stable reference system so signals can communicate without any loss. Electromagnetic theory in reality is very simple if you conceptualize what Maxwell tells you into Ohm's law. PCB designers need to look at transmission lines or a trace between components. If you shrink a trace to go between a pin field, the fact you physically change that trace, you raise the impedance, you have a loss plus reflective waves. So designers need to be aware of how do they route a trace. Is it properly referenced to a plane at the same potential for its RF return? Could be power or return, it doesn't matter. Placing components in an area of high bandwidth versus low bandwidth. The necessary separation of analog and digital. Layer stack-up assignment in order to have the optimal impedance and the maximum amount of power distribution or interplane capacitance. Location of the capacitors, And a capacitor does not need to be next to a pin physically. It could be anywhere in the middle of the board if you have via straight down. Capacitors charge the planes, component consumes power from the planes. So there's lots of rules that are either valid or invalid depending upon application. But it's understanding fundamental electromagnetic theory using Ohm's law. Look at how your transmission lines are routed, and do they have a good RF return path? And you have proper power distribution. That's the majority of the noise that I see generated on boards and why boards have to be respun. Is there a way to resolve EMI issues at the outset? Yes. First off, understanding basic transmission line theory, and look for the three primary items that I had mentioned, which is having a stable power distribution system, the RF return path, and grounding. Simulation is excellent to give you an insight into what may occur, assuming, and that's the key, assuming you have the models. Simulation in the frequency domain will give you a pretty picture of what would occur, but it does not tell you what created that energy, only what may happen. And if you simulate something and you see all this noise over here, the actual source may have occurred here with some coupling, get propagated, and now the via is radiating because of an impedance mismatch or something else goes wrong. If you can get excellent SPI simulation that shows you have high quality signal integrity, chances are the EMI that's created as a result of poor signal integrity will be minimized. So you need to simulate before you do the board layout. After the board layout, basically simulation is useless because you have a board and you're going to spend all your time trying to simulate something that you may not know with all the parasitics. Parasitic capacitance. What if you put a cable on? What kind of cable? Is it put inside an enclosure? Plastic enclosure? Metal enclosure? There's all these variables that are unknown. So we prepare ahead of time. We do the board layout correctly for all the design requirements and rules for manufacturing, testing, and mostly functionality. And then if you have a problem, you need to go in and look at the schematic and the artwork, find out the area where the problem occurred and how to create it, the physics behind it. And to my knowledge, knowing all the books that are out there and knowing almost every author and professor in the world, within here, the book EMC Made Simple, it gets into the physics of what actually creates the energy. And if there is a problem in the frequency domain, an EMI problem, I'm going to use EMI because we're not talking about immunity, a spectrum analyzer only tells you the presence of a field. If I have a problem, I solve it with an oscilloscope because I go to the time domain to look at the characteristics of that transmission line. So I see a glitch, ringing, too much loss. In the time domain, the magnitude of that time domain will create common mode in the frequency domain. And common mode is nearly impossible to simulate. You can observe the effects. But let's get to the source. Basically, what I would like to see more designers be more cognizant of is layer stack up. If you don't have the proper layer stack up and the dimensions, you may not have proper power distribution or optimal power distribution or impedance control. And also the physical science, material science. For the higher speed circuits, FR4 may not provide benefit, but you have to go with a different type of material. Don't just think about cost. If you take it low cost, chances are it's not going to work. You have losses that are inherent within the board materials. So you have to choose the right board material, you have to get the right layer stack up, and then you have to understand the difference between high bandwidth area, the areas that create all of this high frequency noise, and the low bandwidth, so you don't have these talking to each other, or basically the high to the low, and then that goes out on your interface. now you got to add more filtering, more shielding. So it's really application dependent. But you have to know what are the optimal design requirements. Rules of thumb are good to get you into the area, and then you need to either simulate it or actually know what you're doing. And to know what you're doing takes many years of practical experience.